Так. Сейчас. Ух ты, мох ты. Я хотел по-русски говорить. Сейчас, просто сюда теперь, да?
Вот ты длинный, чтобы у тебя это самое...
Вот это? Нет, это туда, да. Вот это.
За уши. Не обязательно. Вот этот длинный запихни за воротник. Вот это.
Он не зайдет туда.
Где очень идет.
Да. Сейчас. Мне ничего не нужно, да? Не могу. Это сюда так. Давно не было у тебя, поэтому. Полгода, да.
Давайте напишем.
Да.
Okay, this is a reference to the file to which will be used during the talk. So when the speaker will refer to some formulas, please have a look at this file.
Mm-hmm. Have you begin?
Mm-hmm.
Okay. So, what I plan to discuss. Really, there is different approaches to thermodynamics. I mean, mathematical approaches. The first one is, we may say, original. It goes to Gibbs, to 1870 or something like this. And he proposed some expression. You can find this expression on the first page. It's called Gibbs thermodynamic fundamental expression, and it looks like this. So this lattice E means internal energy of some system, T temperature, S entropy, P pressure, V volume, mu it's so-called chemical potential, and M is mass.
Mm-hmm.
Yeah. So it looks strange, really, because if it's arbitrary, say, variables, then it's impossible to have such relation. So it means that it's satisfied not everywhere, but on some special surfaces. And it's the best way to understand this is the following. So we just write it as some differential one form. And then this is the expression we should understand as the omega equals 0. And it happens in the space where we have coordinates E, T, S, P, V, mu, and M. And then the right understanding of this is that we're looking for some submanifold in this space. It will be, in short time, it will be some, I will call it's a thermodynamical phase space. And really, this fundamental relation means that this form should vanish on some submanifold here. And by the way, the first reaction on the publication of Gibbs was done by Maxwell. He represented these relations, trying to understand state equations for water, and he drew some picture. No, he just prepared some model of this L and make some copy of this model and send it to Gibbs with very nice words that explain it how important it is and how beautiful this construction. So on the modern language, it seems not so weak. So we're simply looking for submanifold in this space phi, where our form vanishes. So-called integral form, integral manifold, submanifold for this form omega. And if you forget about the meaning of all these letters and write, I will say, formal thermodynamics. So it will be just without any physical meaning, just simply expression like, so y and x is just some vectors. And I will assume that this is vector in some vector space V, and this guy is a vector in dual space, just to make sense of this expression. And you recognize this, so just exactly this expression. So this is our Z, and this is just the rest. And what we know is its form-defined context structure in our space 5. It's V plus V star and plus R. So here X, here Y, and this is just Z. So this is odd-dimensional manifold. This is one form of the dimensional manifold. So we're coming to context. So this is context space. But this form, in Gibbs interpretation, it's not like this. So it's not some formal. It's really expression of few forms. So this is internal energy, differential internal energy. This guy, it's so-called heat, namely as you introduce when you divide the differential of heat by T. This is form also have meaning. This is a mechanical walk that you will get if you just will compress the gases. And this is chemical energy. So all these forms, this is simply forms that respond to some forms of energy. And this is really expression, fundamental relation. It's simply some form of the standard law in physics. It's conservation of energy. So, but this is expression is pure geometrical. So yeah, odd-dimensional space with such form, and then the property of this L, that omega on L equals 0. It's not all construction because we have a lot of such L's. We have this L, then we can take submanifold in this L. It also will be manifold that satisfies this condition, and etc. So the requirement that we should try to find this L that have maximal dimension, possible dimension, maximum possible dimension that satisfies this property. such manifolds we know. It's so-called Legendrian or Legendre submanifold. So this is conservation of energy law leads us to this contact geometry and saying that now for us media or substance that we just working with, it's simply Legendre submanifold in this phi. So when we talk about gas, the ideal gas, it's one Lagrangian Legendrian manifold. If it's water, it will be another Legendrian manifold, and etc. So really, from thermodynamical point of view, these all substances that we work with is just simply some classes of Legendrian submanifolds. So this is the first step. So I hope that for mathematician, this part is more clear than the first one. The second, and what we know that this maximum dimension, if this V has dimension n, then this has phi has dimension 2n plus 1, and Legendrian manifolds will be also n-dimensional. So it means that we, when we say Legendre, we should say that it should be integral for our form omega and has dimension half dimension of 5, so just dimension n. Yeah, it's the first step. So it's just say energetic approach to thermodynamic. This is very formal. We just in terms of contact geometry. There is another, this third approach. So this is the second, and this is the first one. So the third is based on what is modern language, it's information geometry or geometrical statistics in Kolmogorov terminology. So what it is, we consider a random vector with values in our vector space V. So omega, this is probabilistic space, so just space together with some measure. Let's say to be mu0. I am sorry for this, it's not this mu, to x. And we think that result of our observation or result of our measurement, it will be mean value of this random vector. So E is, I'm sorry, it's like once more, it's not the C, Ex mu0, so mean value. So, and we'll just think that when we measure, observe this vector x, so usually what we do, we just take some integral of summation of values and result, we think that is results of our observation or result of our measurement. And so the question that the following, so yeah, it's okay. But we can play with this mu0 and say, if you just take this for given mu0, then this is, and this is our assumption, really, I will assume that it's not, it's a notation, but I will require that this a priori measure, or prior measure, is such that the mean value will be simply 0. It's centered. But now the question...
Do you want that this is expectation value or not?
Huh?
Do you want that this is expectation value?
Yeah, this is okay. It's expectation value, but then I can say
that should be probabilistic measure.
Yeah, it's probabilistic measure, but I will start with some measure, prior measure with 0, such that this expectation will be 0. You can take any measure and think that it will be our prior measure. If it will be not 0, just simply subtract from x. expectation, and you will get 0. Okay. So, but now let's put another question. So, is it possible to find this measure mu such that this expectation will be given vector v? So how to organize this randomness in order to get the given vector v? It's just fixed vector for us. And the question how to find this is mu. So what we will do? Yeah, first of all, I will assume that all measures for us will be continuous. So I will think that mu is a proportional to mu0, and this is density of mu with respect to mu0. So, and now the question, what we can do? So there are possibly there are a lot of such measures. We don't know. Maybe we have no such measures, but if we have, then it's not clear that mu and v will be just in 1-1-2 correspondence. So we will try to find this measure such that this condition, and one more. Assume that we consider all possible measures that this expectation will be v, and from this set or class of measures, we should find the best one. So if you will have, say, a set of our measures, so this mu0, this mu, this one measure, this another measure, so maybe the third one. So the question, can we find in some sense the best or the more optimal measure for us? Yeah, for this we should compare one measure mu, say measure 0, try to estimate some kind of distance between these measures, and this is very close to notion of entropy, or is so-called information gain. Is the following expression. It's integral if you take a logarithm d mu, not the mu0, it's our rho, and integrate with respect to mu. So, and this is integral over. So this guy, it's so logarithm has the same meaning that when it introduce entropy in probabilistic terms, you also take mean of logarithm, minus logarithm, in order to get something positive. But now I will take this one. So what is the properties of this E? First of all, it's non-negative.
It looks like a possibility of, you have the channel and you have.
It's why information theory. This is has a real some information sense. But for us, it's just simple expression. And what is this expression important? What are the properties of this? First of all, it's non-negative. The second, if you will get that is equal 0, then it means that mu equal mu0, and it's common in such situations to say that it's almost everywhere. So in some sense, this is function. It's compare us to. It's give us option to compare two measures, say mu and mu0. And now we can say, okay, we'll take all possible mu where integral of x d mu equal v, we fix it. So it's a subset of measures. And now we can say, okay, let's think that it's not really distance between mu and mu0, because it's positive, and this condition it's non-negative, and zero only when measures almost everywhere coincide. But it's not a measure, not a distance, because it's not satisfies the triangle inequality, and it's not symmetric. If you change mu and mu zero, everything will be changed. But anyway, it's some way to compare two measures. And so we will say that we will try to find such mu that mean will be our vector v, but it should be mu the smallest in sense of this information gave between all possible, the more closer to mu zero measure mu. Probabilistic measure mu. Certainly it should, I should write also this one. It's every time I will tell about probabilistic measures. Okay, and now if you open page number 2, it's where the problem that I formulated is some kind of variation problem. So find measure mu such that this is mean will be v, and such that this expression will be minimal with respect to all possible mu's that satisfy this condition. Probabilistic measures satisfy conditions. And то же самое везде. Значит, on the page number 2, I think, you will find the really solution of this problem. And so this calls principal information gain, minimum information gain. Certainly, more for me, it's more attractive if you will call it this principle of Occam razor. And solution of this problem, it's very simple. It's just so the measure, the distance, the density, this measure mu with respect to mu zero, has the following form. So this is a function on our probabilistic space omega, and this is how this function computed. Lambda is element of dual space. So this measure really, you can say that it's labeled by some parameter that belongs to dual space. Z lambda is what in physics they call, not exactly in this situation, but usually such type of integrals they call partition functions. It's integral of lambda x d mu zero over omega. So yeah, I remind that x is a random vector, so it's a function on the probabilistic space when we integrate on omega. So this function on space omega, and it depends on this lambda. So if this integral exists, you can write this integral and you'll get some values that lambda. Yeah, so certainly this means that this function, this partition function, really in physics, these functions appear when not in such situation where x is some random vector. It appears in the case when x is an energy of some levels. So if x has sense of energy, then such expression in subphysics they call partition function. And also, certainly, it's not true that it's exact every time. So for lambda equals 0, say we will get zeta of 0, it's 1, because it's simply integral of our probabilistic measure. And that's all. But we have really not all possible lambdas, but the only we can say that lambda element of this one. Where this function defined, it's every time question. Okay, so and now this is definition of rho, but now how to,
Well, do you need some constraint to get this solution? Rho 1 over z x.
you mean this one?
No, you have this functional
Yeah.
right hand side.
You mean this one?
Functional. If you write it in terms of rho ln rho,
Yeah.
then you should some constraint to get this rho solution. So variational.
Yeah, you can write this as a functional on rows.
Yes.
And now you have functional on this density rows,
Yes.
and you have also this condition that this integral equal v, and this is another integral equal 1. So it's really this lambda that used here. It's came as a some Lagrange multiplier for this type of constraints. Yeah. Okay. So now how to find desired vector v, and so this vector v is the derivative of some function h over lambda. This function h very simple. It's simply natural logarithm of the function. It also depends on lambda, and this is just logarithm of partition function. It's easy to see that if you just write this integral in terms of this function rho, you will get exactly this expression. So if you differentiate this in lambda, you will get the necessary path for computation of mean. Okay, I will call this function Hamiltonian. Is the first one. The second, the question, what about information gain? If you take this for this new, I will know this mu lambda or rho lambda and mu lambda, this rho lambda multiply on mu. So I will take integral information gain for this new measure mu lambda and measure mu 0. It's also some function that really depends on lambda. But I will assume that we can convert this expression and get it from this lambda as a function of e. So it means, say, second matrix of second derivative should be non-degenerated. Then we can use inverse function theorem. So let's write this, but I will do not by e. I write as a function in v, not in lambda, but as a function in v. And let's so this information of information gain for these two measures, but as a function of this v. Then you can get from this very simple expression that if you differentiate this function in v, you will get lambda, and you will get the following picture. You will see very soon why Kolmogorov calls this geometric statistic.
Because it's Legendre transformation between
Yeah.
Legendre and Valentin.
Really, you will get the following picture. This is our v. This is our v star. Then, if you will write, well, that should be for 0. Say lambda. No, that's with the first equation there. Yeah, v equal dh d lambda. So this space, this coordinates x, this lambda. So what you see, this what I think I hope that you know the notion of Lagrangian manifold. So this is n-dimensional, but Lagrangian manifold. More, if you introduce this function L, you will see that this is so manifold. You can also define as a lambda equal dl dv. And between these two functions, very simple relation, h plus e is lambda v. It's function of v, it's function of lambda, and the sum it's also can be checked. In other words, function a, function h related by Legendre transformation. And this is we will call Lagrangian function. You know that in classical mechanics, when you have Lagrangian, Hamiltonian, they related exactly this, linked exactly this connection. So this is interpretation of problem of measurement of the random vector. But if you have this geometrical picture, you can recognize your random vector. Because from this picture, I easily will find function z, because z it will be simply exponent of h. When you get function z, I can define density. So for random vector, and also all thermodynamical properties that you know about random vectors, they can be now formulated pure geometrically. So the only that we need to work out statistics, we should use only we could, and we will use only. Вот, спасибо. Повесили. So what I wanted to say that really this is pure statistical problem when we just playing with random vectors, with means and so on. It just can be formulated in terms of the geometry. So Lagrangian, it means that you can take this form d lambda du. Now it's your choice. You can continue to work with the notion from statistics, or you can use notions of symplectic geometry, because this is just the trivial part of symplectic geometry. Okay, but there is two things that we can introduce for different application of the first Gibbs approach. The first, what we know that, okay, we know that mean of this random vector is just our v. What we can say about second central moment, sigma 2 x over mu lambda. So mean value of this, it will be just our v. What about the second central moment? So expectation of x minus v. The answer very Ой.
Ну, уже все.
Уже все, да? Окей, sorry. Okay, so we will get this one. So it's second central moment. It's simply Hessian of function h. We can or if you want, we should take x minus v. Now take tensor product on the x minus v and take integral of this d mu lambda and over v, and this is our second central moment. It's if x simply scalar valued random scalar, then it's formula here. Instead of tensor product, you write simply product of two functions. But we work with the vectors, so for this we'll use tensor product. But what is funny is that this element you can understand like this. you can understand that this element of symmetric power of our space V. Or you can think also, so when I write Hessian, I mean the following is sum of second derivatives d lambda I enter d lambda J. So lambda, this covector is coordinate, but d lambda is linear part of this. So you can think about this as an element of vector space. So this from V tensor E. And also, if you change I and J, it will not change it. So it's symmetric. So this really element that you write here, it's symmetric power of V. Or symmetric power of V, you can understand also some as symmetric differential form on V star. So it's also sigma 2. It's some differential form here. Sigma 2 of x. And by the way, the meaning of this form is very, very transparent. So if you take tangent tangent plane to our manifold at some point, then it will be a linear operator between V and V star. Lagrangian manifold means that this operator will be self-adjoint. And so it means that this tangent plane is represent a quadratic form. And this is this form. There is also a Hessian of L, but it will be simply a Hessian of H, an opposite. So if you consider this tangent plane as a linear operator from V to V star, it's a one way. And if you consider the operator from V star to V, it's an inverse of this. So it's this relation. If you want on the level of matrices, it's simply they inverse each other. But if you consider the quadratic differential forms, you also can think gets the same. It's a quadratic form on the V star, and this is on V. This is on V star, and this is on V. Okay, so it means that in this geometrical picture, we have something more. Namely, we have this is the quadratic form. It's, as you know, this is really will be quadratic form, but it will be a positive definite, right? Okay, like dispersion in one-dimensional case is simply non-negative. And so the same we can say about both these forms. If they define it, they at least non-negative. And for us, it's important because really Chebyshev inequality allow us to estimate error that we can get in our measurement. So you remember that with terms of the Gaussian, you can say with this probability, I don't say 90%, you will be in some small ball around V, and this is the size of this small ball will be defined by these Gaussians. So conditions that we will get here, that Gaussians H, it should be non-negative, at least that. But it's also equal 0. It's negative, it means that something wrong in the geometrical pictures. So such points should be removed from our manifold, because if it really came from a random vector, then they have to be non-negative. So it means that we should take this Lagrangian manifold and remove all points where Hessian either 0 or degenerated or negative, and leave only points where this Gaussian will be positive. So it means that it's some convexity of our Lagrangian manifold. Very soon we will see that when we apply this is not for this problem, but for our initial problem, when this space that we came not from this form of stochastic vector, but from say Gibbs forms, we will have the same phenomena. We know that, remember that state equation there, it will be some Legendrian manifolds. But if you take if you add here one variable more, namely information gain, then it will be an added information in this form. You will get Legendrian manifold there. And this is simply a projection of this. So it means that Legendrian manifolds that we get in this picture and Legendrian manifolds we get here, they somehow related. But this from the point of view of statistics, we know that it should be positivity, and when it's negative or degenerated, it's very bad. When we take simply experiment, takes some real, say, ideal gas or van der Waals gas also, and draw this is Gibbs forms and repeated all these constructions and write the correspondent Legendrian manifolds, we will remember, we will get that really points where it's Gaussian zero or negative, it's bad points for thermodynamics, and namely the points where Gaussian just becomes to be degenerated is so-called coexistence curves of submanifolds on our manifold, and more they just predict that something happens with your substance when it just will cross this submanifolds. Namely, it will be the source of so-called phase transitions in thermodynamics. But anyway, I will connect really the first Gibbs. It is formally they connected. This picture and picture that we had for Gibbs form, they related each other. The only that we didn't have this picture. We didn't have random vector and so on. But I said that if you have this picture, you can reconstruct really everything. You can reconstruct this random vector and densities, probabilistic measures, and etc. So it means that if V and V star will have the same that in thermodynamics, in energy approach, then it corresponds to random vectors, or it means that elements of V, they are random for us. And this manifolds that we simply wrote, it's simply a geometrical interpretation of this randomness. Okay, so it means that we should consider this Legendrian or Lagrangian manifolds, but also think that there is some kind of metric, at least in a domain I will call points stable if Gaussian will be positive. So on this stable points, on this subset of stable 2 points, we will get simply on this manifold Riemann structure. So really, the part that we will work, we will use, is simply Legendrian or Lagrangian manifolds together with Riemann structure on this. It's the first observation that we just will get from these 2 parallels. And one more, here we use it natural logarithm, but I can write here logarithm with some base A. In information theory, it's called information units. It's E, it means that we measure our information in knots. If it will be 2, it will be in bits. And for any A, not for any, but for some A's, there are these new names for this information units. Now the following question. Okay, if you just will work with the Gibbs approach or with this formal approach, So what happens when we just change base of this logarithm? It means that this is I will be just multiplied on the change of base, the logarithm, say, not natural logarithm of a. So, and you can see on our formulas, you will see really that v will be multiplied on this element. V also will be multiplied due to this formula on this element. So L also will be multiplied, and etc. So it means that in our picture, change of this information units will produce the following transformation in this formal language I just will write. So x goes to lambda, not lambda. I don't know.
Mu.
Huh? Mu. Sorry, the problem with languages. Okay, alpha x. X goes to alpha x. Y goes to y, it will not change it. Z will go to alpha z. So we deal with this rescaling in this variable. So in physics, they have name, it's called extensive variables. They said that they depends on size. So if you just change size, it should be multiplied. And this is intensive variables. They don't change the size. And if you will see on this one, and look at our form omega, you see that if you multiply z in x on some number and don't touch y, it will be contact transformation. So it's some kind of contact transformation that just multiplied our form omega also. But it's if this Legendre manifold, it has meaning of some physical law, like when you write, say, laws for ideal gas, I forgot what is the names. All these expressions that they wrote to define this Lagrangian manifolds, they have names. So you can simply say that this is L for us from a physical point of view. This is a physical law that show us how our media will behave in thermodynamic processes. And it will be very bad if our physical laws will be depend on base of units of this in which we measure all these quantities. So, so this is the first principle. It's in thermodynamics. It's very often they use it that everything that will be written and where you will have lambda, we have z, x, and y in slightly different is the physical notations. But if you multiply z and x on the same number, then the law that we use should be unchanged. So it doesn't change our physical law. But how to say this in our language? So this is contact transformation. The vector field that corresponds to these transformations is, I will write big Z, is the following vector field. It's x dx and plus z dz. Right? So this is exactly a vector field that's responsible for this type of transformation. And this contact vector field. Once more, let's go to contact geometry. In contact geometry, we know that if you have contact vector field, then this contact vector field completely defined by generated function, by value of our form omega on this vector field z. If you just computed this here, so it will be z minus yx, right?
Very sympathetic.
Yeah, and this is in thermodynamics. This is functions appears very often, but not in this context. Simply, time to time they use this expression. It's once more goes to Gibbs. It's called Gibbs potential. And in notations, when we define H, if you say that any contact vector field defined by generative function, you write the contact field corresponds to function H, say, as a Hx. It will be exactly our Z with this condition. Okay, so it means that behind this geometry, we have, this is our metric on Lagrange manifold, but this Lagrange manifold should be invariant our transformations, our shift along Z. So L should be Z invariant. Once more, go to contact geometry. We know that when it will be Z invariant. So vector field, it's tangent to our manifold. Our form omega equals 0 on this manifold. So if it follows this definition, compute the value of omega on Z, then you will see that this function should be equal 0 on A. So really, one condition, this is this one. H on A, it should be equal 0. So we increase the number of geometrical constructions that related to this formal geometry. But some of them are very important for us. So yeah, it's Lagrangian or Legendre manifolds is the one. The second, they are Riemann manifolds because everything that weighs our Hessians negative or degenerated, we simply remove it from consideration. And it's also our space equipped with this contact vector field, and this contact vector field tangent to our Lagrangian or Legendre manifold. So now let's try to write. I think that's enough. Right here. So this is our space. I will continue with this 5. We will back to Gibbs formula, but it will be the same V with star simply instead of X, Y, Z. It will be this lattice. Okay, at least in these pages that you have, you can find relations between this X and Y and physical notations P, T, S, and so on. So this is our space phi. So V plus V star plus R. So this is a picture. So here I will change my mind. We will start here, V here, and this is R. So this is Y, here X, and here Z. By the way, Z it will be proportional to entropy that we used in simply will be minus entropy that we use it in Higgs formula. And in this space, we also have, so our manifolds that we will use, they're not arbitrary. They should be belongs to zeros of this function H. So we should write here. It's very difficult. Okay. Right here, this submanifold H equals 0. It's codimension 1. And you see that it simply said that it's Z equal Yx. So this is our manifold. And so L, it will be something here, this L. Now, let's see what happens if you just continue this picture. And now the more important geometry will pop up. It will be geometry of jet spaces. Instead of contact geometry and formal, etc., it will be now jet geometry. So I just will remove this. Okay. No, so let's see what this is our L. It's here, right? And but we don't need the form omega because we should stay only. Let it will be, I will call Euler Euler equation or Euler submanifold. So what we need to use not omega but omega restricted on this is submanifold, and you can easily check. So put it instead of that product y and x, you will get simply xy, xdy. So here we have form x dy. So x and y are the coordinates on this space E, and it has dimension 2n. It's dimension 2n plus 1, so this is dimension 2n. And here we have this form. So it's even dimension, but we have differential form on this. If you will be not even dimension, but odd dimension, then we expect that because this form omega should be equal 0 on L. It's still a condition that is Legendre and Lagrangian. It means that the form should be equal 0. So if the form will be on odd dimensional manifold, then it will be okay. So what I will do, I will take this E and take quotient under action of Z. Because, okay, L invariant under Z, so it consists of the trajectories of Z. E also contains invariant of Z, so it's also some manifold that we can think that it's the trajectory. It's not curves, but it's points. So we go to this quotient. It will be, first of all, it will be have dimension 2n minus 1. It will be odd dimensional, right? Now, what happens with our form? So we see that if you put omega, our point z in this omega, you will get 0. Because this condition was h should be on this e equals 0. So it means that our field belongs to kernel of this omega. And our z is a contact vector field, so it means that under shifts, the kernel of this new form, let's call this omega bar. So it means that if you take this form omega bar, then this form equals 0. And also Z is a contact vector field. So what we will do, we take distribution where this form omega 0 equals 0. Then and this is distribution from this from this picture. Will be just go to some distribution on this quotient. So on the quotient we have this the contact distribution defined by omega, this new omega, and vector field also will belong to this distribution. So when you will go to quotient, so this is the kernel of omega, but z in this. So if you just go to quotient, you will get a factor of our distribution by z. So it means that this is a new contact space. Have a dimension 2n minus 1, and the form omega bar, but omega bar, there is our omega. It was simply x dy, right? And so when you apply our transformation z, then you will get x will be multiplied on something, y will be not change it, yeah? So how to get this contact form that will define the contact distribution? It's very easy. Let's call this omega omega tilde. The problem with this x. X is not a function on our manifold E, but instead of x, I will use. Let's write it like this: it's sum of xi's dy's. So I will take some domain where say x, I don't say xn, for example, positive. And you consider xi divided by xn. And we call this xi tilde. Then what happens with this my form omega? Omega tilde, this contact form, but I can consider this up to multiplier. So I will simply divide all these x's on xn. And what I will get here, I will get the following expression, dyn plus sum of 1 to 1 minus 1, x tilde I dyi. So we see that our quotient manifold, it's here it will be not L itself, but it will be quotient of our L. But it will be, once more, it will be Lagrangian or Legendre manifold, because if L was dimension n, then the quotient will be dimension n minus 1. And this is what should be to be Legendre manifold in this one. But new form has the following form. And now what we can say that first of all, how these quotients look like. So if you take this one and we'll factorize by action of our field Z, first of all, it will be act only on these two elements, on V and R. So it should be V plus R, and here we should factorize by Z. V star, we don't touch, so it will be just this. But if you take V plus R and consider this field Z, you will see that orbits are just simply rays in this space. So if you take this one and factorize by Z, you will get simply a dimensional sphere. So this quotient that we're talking about, it's simply V star cross n-dimensional sphere. Yeah, V star cross, yeah. And now, but why it's, sorry. Yeah, so E has dimension 2n. Yeah, so I should take this one, but I should also remember that it should be h equals 0. So we should pick here submanifolds where our function h equals 0. But our function h, this is Gibbs function is z minus xy. So what happens if you just take this function, then it's order degree 1 in z in x. So it means that this condition, then it's equal 0. It will be just invariant under our z. So this is really this our h. So this has dimension to n minus 1 to n, and this is dimension. So this is this one what I said here, and this one it's oops, where is one dimension more? Yeah, so you can see it's here really. So So we have coordinates on this quotient space. I can say that it's simply this axis with tilde from 1 to n minus 1 and y's. So coordinates in this space, it will be this x1 tilde, xn tilde minus 1, and after y1, yn. So the dimension will be 2n minus 1. And in this, now this is a new contact manifold for us, and the image of our quotient L, it will be Legendre manifold in this setting. And if we just will assume for the moment that, so let's quotient L by Z, denote Z, capital Z. It will be, say, L tilde. So this n minus 1 dimensional manifold, and it should be Legendre with respect to this new form. So let's assume that functions y1, yn minus 1, they are local coordinates on this manifold. Then we will see that this manifold will be defined by this relation yn plus some function of y1, yn minus 1 equal to 0. Then if you put it here, then this xi's should be simply derivatives of this function phi. So xi's tilde, it should be d phi dy I from 1 to n minus 1. So this is description of this quotient. So it's Legendre manifold in this new space. And if I will assume that with this y1, yn minus 1 coordinates, then it means that differential that yn should be function of this y's. And this x is with tilde, it will be just derivative of this function phi. So let's call this function phi as a generated function of quotient of this L tilde. So what happens? Really is essential from this picture. Yeah, we begin with a Legendre manifold in this space phi. After we use it, that this Legendre manifold should be invariant under this scale transformations. So it immediately says us that L should be not in this space, but in smaller space, manifold E, this L manifold. Then this manifold also invariant under Z. So if you go not, we'll consider not our L, but we'll consider quotient of L by Z. Then the quotient of this is L tilde. It will be defined by some function of n minus 1 variables. Why is that? We pick it yn, but it function was from y1, yn minus 1. And equations will be the following. So this is equations for this quotient y's. It's also, by the way, with the quotient, so this integrals our z, our action of z. So everything now z invariant. What you can do more, you can try to find, because our manifold, so we used it on our Legendre manifold only one property, that it's invariant under scale transformations. But we had also quadratic form Riemann structure on our manifold. So this also will go to this one. I will not go in details, but what I want to say is that it will be simply, formula will be simply Gaussian of this function phi, like it was in general case. Okay, so now where is jets? So the situation is the following. really this one, this one, this is our E. It's where h equals 0. In this space phi, and space phi, this is sum of these three vector spaces. It's remind you one jet space, right? But the question functions on what it should be considered here. Either functions on V, then V star will be cotangent space to V. But if it will be V star, then V will be cotangent space of V. And this is R. So the R, it's really play of role of this function H. So Gibbs function, it's like this our function U in definition of one jets. Now our choice, what we should take, V or V star as a base. And this is computation show us that really we work with one jets function or on intensive variables on wires. So it means that we should take V star as our base manifold. Then what we see here, this L tilde, it's simply submanifold in this V star, but let's call this say N, and the codimension of this equal 1. Then our space E, it was V plus V star. Not exactly, but say V plus V star. So we'll see about this as a tangent cotangent bundle to V star.
Tangent or cotangent?
Cotangent. Tangent will be once more V star, but cotangent will be V now. So this is cotangent part and this is tangent part. So I have here my n-1 dimensional manifold. And to recognize our manifold L, what we should do, and this is like we take our function phi, and now we take simply one jet. So we should take, this is submanifold of codimension n-1, and they take simply the one jets of this n-1 dimensional manifold. So what is mean one jet? We should add a tangent plane here, right? To have one jet. Tangent plane, it's can be defined by form that vanishes on this tangent plane. But form here, it's exactly because we work in T star, then form here is simply vector. So annullator of this n-1 dimensional tangent plane will be vector. And this is our vector Z really. So really construction that we use it to recognize our initial A, it's simply this n-dimensional manifold and one jet of this. So really this is A to begin with. It's simply one jet of some one-dimensional submanifold in V star. More, you see that if you have this this submanifold, you define this manifold say in this form. So it's a graph of say some function on n-1 variables. Then this is formula simply give you the complete description of your L. And then it means that the situation exactly that you meet in jet geometry. So you have this is n-1 dimensional submanifold, and you take simply one jet of this. Then you will get the submanifold L, and this is just our wave space. So instead of working with this n-dimensional and blah, 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 it's enough to work only with n-1 dimensional submanifolds in V star. And what is important here, that you see that our state equation now have this form. Remark that this xi's with tilde, the invariant of that is the first integrals of that. And we defined them by simply divided xi's by xn. It's what happens in thermodynamics every time. They use mass, they use volume, blah, blah, blah. But after they go to specific values or densities by division, specific division by mass, densities when divided by V. So really this practically only this X tildes use it in description of state equations for gases for in thermodynamics really. So really this is existence of this Z. It's important part of thermodynamics because it's explain why and how to use really this is quantities, specific quantities, or say densities instead of physical quantities. This is volume, say you can use simply specific volume, or instead of say mass, you will use density and so on. So it's now the situation is critically really changed because first of all we're working with this very simple pieces of our geometry, only with these ones. But what we know that behind not only first jets we use the second jets, third jets, and so on. Now we just goes to very attractive part of thermodynamics, is called so-called phase transitions. There are different understanding what means phase transitions. I will not go in history of this definition, but I will prefer to use Ehrenfest definition of phase transition. He says that if some physical quantities first order change it, behave non-smoothly. So in some areas they lost, say, continuity, they lost differentiability. So it means that something not regularity happens with our physical quantities. Then it means that we are in position of phase transition of the first order. In the first order, really, what kinds of in derivatives, what kinds happens with kinds of non-regularity? It's when the first derivatives can be just jumped. You have some situations where say like this. So first derivatives just simply jump it. But we also know that it's very possible that you have very good first derivatives, but second derivatives we have ugly. So it means that under prolongations, it's very possible that not first derivatives, but second derivatives will be also behave non-regularly. So it means that you will have phase transition of second order, and etc. By the way, with first derivatives is more or less obvious. So it means that if you take this Lagrangian manifolds and Legendre manifolds and project on this variables y1, yn, and spine, this projection will have singularities. It's what Arnold studied, Arnold's singularity for projection of Lagrangian manifolds. So the first transitions is exactly in this picture. It's simply what Arnold called singularities of projection of Lagrangian manifolds. There are a lot of interesting things there, but I don't want to discuss more this phase transitions. It's a separate topic. But I also promise to say, do I have time? About thermodynamics processes. First of all, from geometrical point of view, what means thermodynamical processes? It's some kind of when all thermodynamic quantities change smoothly, but they should preserve this fundamental Gibbs relation. So they should preserve zeros of this form. So it means that this should be flow along contact vector field. So it means that physical thermodynamic processes simply flow under some contact vector field. But we should remember all this construction. So together with simple notion of Lagrangian manifold, we use it also this invariant conditions to be invariant under this vector field Z. And the second, it should be good respect to this quadratic form. I will skip for a moment quadratic forms, but about Z. So if you just, I will say that it's Gibbs-Duhem principle, because there are not such principle in thermodynamics, but there are a lot of equations of the first order, where if you just consider them, they will every time will mean that the quantity should you consider should be invariant under Z. So now we talk about state equations of Lagrangian manifolds, Legendre manifolds, and invariant under Z. Now we talk about thermodynamics processes. But if you just forbid it to use simply Legendre, but requirement that it should be Z invariant. So the same we should do with contact transformation. We should consider contact transformations that commute with our Z. Right? Then if they compute, then they satisfy our Gibbs-Duhem principle. So Legendre Lagrangian manifolds Z invariant and contact transformation commute with Z. Then you will write this condition. You will easily understand that F should have in this notation that sum of A's i's on y's x i's plus b y on the z. So it means that our function F should be linear function in this is extensive variables. And coefficients dependence on y. Then this is vector fields xf. It also can be moved on our new situation when you have simply everything on V star. So it means that if you take this xf and take quotient of this, you will get vector field really on V star. And this vector field you can find on these pages. I forgot where is it.
Page 6, I think.
6?
To my opinion, yes. Item 10. Page 6.
Yeah. And this vector field is sum AI's plus B.
It's page 6.
Yeah, it's sum AI's
0.10.
of y plus b of y on y of i's and d dy i's. So this vector field really is not vector field on it's all vector field on our phase space, but this condition that you should commute with z also lead us to this vector field, and this vector field now on V star. So you see. Our state equation we formulated as n-1 dimensional submanifold in V star. And thermodynamic process we also formulated, we can formulate like this as a contact transformation, blah, blah, blah. But now you can say that it's simply a vector field on V star. And if you want to have thermodynamics process that goes in some media, and this media divided by our L, then it means that this is vector field that we here wrote. So this is xf tilde. So this vector field should be tangent to our n-1 dimensional manifold. So this immediately gives you a very simple formula to description of thermodynamic process. they should be vector field on this manifold that tangent to the tangent to this. So there are simply they depends on n-1 function, right? So we should simply write this expression, but for n-1. Okay, and the final remark, it's about what means control thermodynamic processes, how to control them. So first of all, how to understand what is a control. Say we have something, say heating or cooling, or we compress your media, and how to control this. You should influence in some way on this your process. But how we can do this? It's not like they do in control theory that some parameter can be changed. No, this simply flow, and you want to change in some sense them, but you don't want to destroy this process. So the trajectories of your process, they should be the same trajectories, but it means that we looking for another thermodynamics process, so another contact field, but with conditions that this vector field will preserve trajectories of our process. So we can say that if you have, say, processes defined by contact vector field x f, then we're looking for another vector field xg. And what is the condition for this? So really commutator xg and xf, it should be proportional to xf with some coefficients here. I'm sorry, I used lambda many times, so I will put once more here lambda xf. So this is a condition for control. So this process xg will control to xf if you will change our xf by multiplication on in this case simply by multiplication on exponent of lambda. What you see that we still will think that xf and xg they commuted with z. So it's also commuted, so it means that this control process will be once more vector field on this n-1 dimensional. And this is condition that we write here. It will be goes to conditions of this quotient. And first that you can easily check that you have this commutator for contact vector fields, lambda will be constant. It's not function, it will be constant every time. And okay, and so if lambda equals 0, then it's simply symmetry. It doesn't change really our process. And if lambda is not 0, it's say lambda positive. It means that we will increase speed of our process xf in exponent of lambda time. And if it's lambda negative, then it will be decreasing of velocity with the whole. So it's like driving of car. So when you use this xf, xg, then you can play with this lambda. So if lambda positive, then xg will be just increase our velocity. If it's you change lambda negative, and this is a condition. It's simply differential equation for this function g. You can find in this pages. You can find this equation. It's really a linear differential equation of the first order, and really it's solvable. At least if you take, for example, if you take adiabatic processes, then it's simply solvable in quadratures. Okay, is the second time. What else? Yeah. And so if you consider, say, let's call this controls of weight lambda. So if you take two controls, then you can take the commutator. It's once more will be controls, but it will be with lambda equals 0. Lambda equals 0. It's symmetry. So really, the set of controls will be Lie algebra with respect to this bracket is Legendre brackets. But in controls there are also symmetries that really do nothing with our processes. They simply preserve our processes. And commutator of two controls it will be just once more symmetry. So this You have big algebra, algebra of symmetries. Inside of this algebra, you have symmetries, and commutators of controls goes to symmetry. So it's just commutator of this algebra. Commutator algebra will be simply algebra of symmetries. Okay. Maybe the one last remark that I think I have to do this. It's what happens if you take some simplest case, ideal gas. It's for this gas you can I don't remember. It's easy to really compute it. Simply I want to give you answer. The answer that this function phi that we use it here. Where is this function phi? It's t.
Page 5.
It should be
09.
P and T or not. Oops.
Page 5, section 09.
It should be T in some degree and there is where is this?
Maybe it's 8. P
Ты
equals
про идеальный газ
1
говоришь?
T.
А?
Про идеальный газ?
Да.
Ну вот он.
Ну там фи должна быть функция фи написано. Фи.
Page 6. Five.
Yeah. 5 equal, yeah. So this 5.
Yeah.
It's 5 is the following. It's some constant C1, Y1, it's T, in temperature in degree 5, 2, and yeah, exp of Y2, this is temperature, and this is chemical potential divided by R Y1. So this equation, this is formula. There is a C1 here. Just below there are expressions of P, sigma, and rho. But what is important that new constant C, it's not universal. This is universal gas constant, but this is C1. It's a new constant that came here. And what is about C1 is the following: that if you take T and tends to infinite, then say pressure will go like where is C1 on T in degree 5. Yeah. So this C1 defined is the following way: if you will increase temperature, then pressure will be changed in this law, and C1 is exactly this constant. So it means that really the definition, when you write conditions for ideal gas, simply for gases, they use it only P, T, and that's all. And there is another intensive variable, it's chemical potential. So if you include chemical potential, then new constant will appear. So in our description, and this is constant. It simply shows how behave pressure when we will consider big temperatures or higher temperatures. Okay. Really, it's require not 1 hour, it's require much more. I'm sorry for some mess.
No, it's okay. It's perfect. So we finished.
Yeah, I have to finish, but I have something to tell you, but not now.
We can, have prolongation sometimes. Okay, thanks a lot. Questions, remarks? Then thanks a lot again.
Thank you,
It's
Tom.
very interesting. And well, next time we meet again here in this room, and the speaker will be Valentin.
Oh.
Goodbye, and thank you for
Yeah.
being here.